Well, good morning, everybody. Rich Fiorella is our speaker today. He's a brand new staff member in the Earth and Environmental Sciences Division at Los Alamos. And the focus of his expertise in Earth system modeling lies in understanding the changes in the water and the carbon cycles and their impacts, particularly through water isotopes. He received his PhD from the University of Michigan and then held a postdoc and a research scientist position at the University of Utah, where he was the PI of an NSF project to develop water tracers and isotopes in CESM. He's been here at Los Alamos as a director's postdoctoral fellow, and during that, he collected and analyzed stable isotope ratio observations with which he developed isotope tracers in ELM. So Rich currently serves as chair of the Atmospheric Isotope Technical Working Group for NEON, the National Ecological Observatory Network, and he is a member of NEON's Science, Technology, and Education Advisory Committee. So, Rich, we're really glad you're here to give a talk.
Thanks, Elizabeth. Yeah, I'm really excited for the opportunity to present some of the ideas I've been working on to the ETHRSM team. Today I'll be talking about some of the water tracer and water isotope work that I've been doing in our system models and how they're useful to help us understand the hydrological cycle and its representation in these models, and then end with some of the opportunities that I think that implementing these tracers throughout ETHRSM would present. This will be fairly forward-looking, as the tracers that Elizabeth mentioned in ELM. I've only been partially implemented at this point, but I'll share some of what I learned from prior work in CESM and what I think some of the unique possibilities for ETHRSM will be. Okay. This slide can be fairly quick because Elizabeth gave me a great introduction, but I'd like to start with a couple words about my background since I've not yet had the opportunity to meet many of you. So as mentioned, I'm a new staff scientist at LAML, and my primary research interests center on understanding water and carbon cycles using our system models and stable isotope ratio observations across a large range of scales. And I've also been very involved in the development and use of the isotope ratio data products from the National Ecological Observatory Network, which is a little described. Gives us some pretty interesting validation opportunities for ELM and EAM as well. And so I'll be talking mostly about the water cycle today. And I think one of the most striking aspects to me about the terrestrial water cycle is just how important the land-atmosphere coupling is to terrestrial precipitation amounts and to water resource availability. So this figure shows a schematic of Earth's water cycle, and one key aspect is the amount of precipitation that falls over land is roughly triple the net water transported from the ocean to the land by the atmosphere. And so these higher than expected or higher than anticipated precipitation rates are only possible due to the large evapotranspiration flux over land, which effectively recycles this moisture over continents and perhaps multiple times. The terrestrial water cycle is also really strongly coupled to the carbon cycle. And one of my favorite depictions of this comes from this Humphrey et al. 2018 paper, where they show the relationship between the carbon dioxide growth rate in the atmosphere. It's just the black line on this y-axis on the left, where more rapid growth rates are at the bottom, and the terrestrial water storage anomaly on the right y-axis, and the line in blue, which is measured by the gray satellite as gravity anomalies over land. And as we can see, they're really tightly correlated and coupled. And so the link here, of course, is photosynthesis and GPP, where GPP is inferred to be higher when there's more water available to plants on land. And conversely, when water availability is low, ecosystems experience drought, which can lead to plant mortality through a variety of mechanisms, which also impacts the carbon balance of these ecosystems, as well as the water cycle downwind. However, while we know that water availability is critically important to ecosystem health and is a big factor influencing the land-atmosphere exchange of water, carbon, and energy, we have really poor constraints on how much of that water actually leaves ecosystems through plants as part of the evapotranspiration process. So this figure is a compilation of this global transpiration to evapotranspiration ratio that I was part of putting together a few years ago. And as we look across the methods, we can see there's a tremendous spread where the median value across the compilation suggests that globally this value might be between 50 and 75%. But different estimation, upscaling, and modeling methods yield values as low as about 25% or lower even to greater than 80%. And so as a result, there's a lot of uncertainty in our understanding of how water moves through terrestrial ecosystems and environments, which translates into uncertainties in kind of the coupled aspects of the hydrological cycle, including things like water resource availability to societies, the resilience of ecosystems to climate change, their risk posed by fire weather. And so I would argue that an important tool to develop would be a new capability that allows us to examine some of the underlying hydrological processes and coupled models in a bit more detail. And I think water isotopes can be, one tool that gets us in that direction. And so for the rest of the talk, I'll go through briefly water isotope ratios and the fractionation processes that make them useful environmental tracers. I'll talk a little bit about how these tracers are implemented in our system models, how the same code can be generalized to track a very wide array of hydrological processes. And that close with a couple slides on some of the opportunities that I think E3SM has some of the opportunities that would be present and uniquely in E3SM. And so, I guess, why are isotope ratios useful for environmental tracers? Primary reason is that different processes cause different isotope logs of water, which have different masses, to be unequally partitioned between components. And the dominant process that drives this fractionation in the water cycle is our phase changes. So I'm showing a schematic of this here where if we have a condensation process and we're removing water from vapor, the heavier molecules in that vapor will preferentially condense, leaving the lighter ones behind, while the reverse is true during evaporation, where the lighter molecules will preferentially evaporate. The primary isotopes that we're concerned with here are the stable isotopes of oxygen and hydrogen. So for oxygen, this is oxygen 16, oxygen 17, oxygen 18, and with the vast majority of it being oxygen 16. For hydrogen, this is hydrogen 1, hydrogen 2, with the vast majority of this being hydrogen 1. And if we propagate these proportions or distributions into what the actual water molecule would look like, we would have about 99.7% of water molecules would have both of these light isotopes, so the oxygen 16 and hydrogen 1. About 0.2% would have substituted oxygen 18, and about 0.01% would have a substituted hydrogen 2 for one of the hydrogen 1s. So if I had a 1 liter water bottle here, about 997 milliliters of that water bottle would have all the light isotopes. 2 milliliters would have a substituted oxygen 18, and about 0.1 would have a substituted deuterium. And while these abundances of these heavy isotopes are fairly small, we can measure them quite well, and so we can interpret pretty small deviations in the ratio of the abundance of these isotope logs. A few points of notation to describe before, because they appear quite commonly, that describe these isotope ratios. So there's the parameter R, which is the heavy to light isotope ratio in a particular sample. So this might be oxygen 18 to oxygen 16 or 2H to 1H. Alpha is the fractionation factor that describes the partitioning of these isotope ratios between phases. And by convention, it's set up so that it's greater than 1, so that the phase with the higher isotope ratio, the higher heavy to light isotope ratio is on top. So for example, here we have one that is the heavy to light isotope ratio of liquid to vapor. And then because the meaningful deviations that we're getting out of these isotope ratios are fairly small, they're commonly expressed in delta notation as deviations from a standard, often multiplied by 1,000 is part per 1,000 deviations from a standard. And the standard commonly used in the water cycle is mean ocean water. So the isotope ratio of ocean water here, right, we would assign a delta value of 0. The most common theoretical framework to explain variations in these precipitation isotope ratios is Rayleigh distillation, which describes the evolution of water vapor and condensate isotope ratios as we progressively remove water from a sample. And so the figure at right shows how vapor and liquid isotope ratios would co-evolve as we remove water in this idealized open system condensation process. There's an initial fractionation between the phases of about 10 per mil when we start, and then as we progressively remove that water from the sample, both the vapor and liquid isotope ratios decrease as less and less water is remaining. Place the Rayleigh distillation equations in the bottom left here, and both in isotope ratio notation here and in delta notation. And there's kind of 3 key parameters that explain the isotope ratio at any point here. The initial isotope ratio, so where we're starting, how far along this path we've gone, so either F or I've placed it here in terms we might encounter. And atmospheric measurements more commonly is Q to Q0, so the initial specific humidity. And then the fractionation factor alpha, which describes the degree of partitioning between those phases. One final thing to note on this slide is that while this notion of F is conceptually pretty simple, it can be pretty hard to define in observations since it's often not clear what Q0 is in an observation that we would take due to atmospheric mixing. So this is something we can define in the model, but it's really hard to measure in the real world. So based on that last slide about Rayleigh distillation, you might then expect if we were to go out and measure precipitation and water vapor isotope ratios across the globe, they might be high in humid warm areas where F might be high, so the fraction of vapor remaining would be high, and it might be low in dry cold areas where F would, the fraction of vapor remaining would be low. And this is broadly what we observe. So I'm showing a map here that's a geospatial regression of oxygen isotope ratios and precipitation, where we can see there are strong spatial patterns in the water isotope ratios in the annual mean based on climate and topography. So delta is low at high latitudes, altitudes, and in continental interiors. And so the Rayleigh model has been the predominant theory to explain precipitation isotope ratios for several decades, despite an acknowledgement that as a simplification, this is not the only process at play, and that the actual Rayleigh fraction on which it's based is hard to define, but we've kept using it because it works well at large spatial and temporal scales. But since then, there's been a bunch of new theories advanced as we've collected more data that hinted at other drivers in situations where the isotope ratios that we observe don't match Rayleigh expectations. So some of these might be upwind precipitation processes and convection, changes in moisture sources that contribute to that precipitation, or the length of time that that moisture spent in the atmosphere, or the cloud type that generated the precipitation, or the vertical profile of moisture entrainment, local moisture balance, or perhaps we just kind of say maybe it's all of these. And so one of the ways we can begin to tease apart the importance and influence of these competing processes is by teaching isotopic fractionation to Earth system models. And so to do this, essentially we build a parallel version of the water cycle in the model that kind of is in the tracer code with a few additional modules that responds to, but does not feedback on the model physics. So it's just a parallel copy that we can kind of tweak in different ways. The figure that I'm showing here is a schematic of what this might look like in the atmosphere model, but we could draw a similar figure for any of the component models. where we build parallel representations of all these water transformations throughout that domain. And so in this example, showing all of the fluxes in the atmospheric model, and any flux that we've modified to represent the unequal partitioning or isotopic physics is shown in red, while every flux in black is non-fractionating. And so transformations in these pools are modified in a way just to maintain proportionality with the bulk water hydrological cycle. And so here are some results of a run in CAM6 using an FCOM set, which is active atmosphere and land, that we nudged to ERA5 reanalysis winds and surface pressure to get the circulation approximately right. And the figure at left shows the weighted mean precipitation isotope ratios, which generally follows expectation of high values in the tropics and low values at high latitudes, altitudes, and in continental interiors. And the figure on the right shows a comparison between site-based means of precipitation isotope ratios and values for that grid cell and the model climatology from CAM6. Across 3 simulations, one in which the winds were nudged to those ERA5 wind fields in purple, one in which we removed that nudging and just allowed the winds to freely evolve, forced on SSTs, which is in orange, and then the CAM5 previous version of the code in green as well. And so we can see that on a long-term basis, there's some spread around the relationship. CAM6 shows an improvement over CAM5, but both models are able to fairly well capture the observed range and precipitation isotope ratios. So now that we know that we have something that approximately represents reality, we can take a look at the relationship between these isotope ratios and the underlying processes. And so returning to the schematic of the implementation of the isotope ratios in the atmospheric model, this version that we've done for isotope physics only represents kind of one possible copy of the hydrological cycle in the tracer code that we could make, where we've chosen to weight these fluxes based on our understanding of isotope fractionation in physics. But we could instead choose to weight any of these particular fluxes by a different property while keeping all the other fluxes in proportion to the bulk hydrological cycle. And so this concept would allow us to create different classes of tracers for essentially any process on this chart and track a wide variety of processes that related to evaporation, condensation, transport, and mixing. And so here are some examples of the types of processes that we could trace through this model using this framework. And so these take a little bit of, I guess, orientation to think about, but each of these panels represent some property of precipitation falling in that cell that might be integrated across all of the possible moisture sources that contribute to precipitation in that cell. So in the top row, I'm showing examples where we're tracking a particular flux. So on the left here, I'm showing the amount of precipitation that falls in that cell that arises from vapor that entered the atmosphere as transpiration, either in that cell or elsewhere, and was transported to that point. We can see it's high near tropical forests and in continental interiors, speaking to that moisture recycling that I described before. On the right, I'm showing a condensation property, which in this case is the temperature at which water in that precipitation condensed, which is useful for understanding isotope ratios and precipitation, as well as understanding energy transport. On the bottom row on the left, I'm showing the mean relative humidity value during evaporation experienced by water precipitating at that location, which has implications for the expected kinetic fractionation during evaporation. And then on the right, I'm showing the mean time the water precipitating at that location spent in the atmosphere between source and sink, which might be important for testing theories of large-scale hydrologic cycle change. And so these tracers can help us better understand the relative importance of those drivers to precipitation delta Q and help us unravel some of these controls in an integrated quantitative way. And so as an example, I'm showing results here from a random forest regression model on time series of precipitation isotope ratios and various drivers that have been proposed, such as that rainout fraction, condensation temperature, the initial evaporation isotope ratio. So these three are the ones in the Rayleigh parameter or the Rayleigh equation, and then a few others that have been described. So local precipitation amount, and then transport distance and residence time. None of these variables would be possible in this regression without the tracer code. They all originate from the tracer code, and so this allows us to connect the model variables to the underlying processes that match theoretical expectations rather than, say, a local temperature, because it's a variable we have. The x-axis is a variable importance, and we can see that running this model globally, the most important variables are in fact this rainout fraction and the modifications to this fractionation factor through the condensation temperature. As a separate application, I'd like to come back to this T to ET ratio quickly and show the ways that this tracer code could be used to investigate these changes in the hydrological cycle. So I'm going to focus on this figure on the right, where I'm showing the percent of terrestrial precipitation that comes from, that originates from transpiration in blue over time versus what originates from soil evaporation and interception in orange. And this is from a simulation that extends into the future using the SSP3 7.0 watt per meter squared forcing scenario. And what we can see is that transpiration decreases in the 21st century, soil evaporation increases. There's a parameterization regarding stomata that's likely responsible for this pattern, and it has impacts on kind of extreme events. And so it's another reason why it would be important to understand this TET uncertainty in the future, which brings us back to the water isotope ratios again, which can be used to place constraints on TET partitioning, because these two fluxes that make up the net ET flux are expected to have different isotope ratios. So evaporation is expected to fractionate, with the lighter isotopes being preferred over the heavier ones. And then transpiration is thought to be non-fractionating because plants don't fractionate during water outtake, so all the mass balance dictates that all the water goes into the plant must come out. And so this would be non-fractionating. And these used to be hard observations to make, but now, I guess with the advent of networks such as NEON, there are new, about 20, 30 sites that we could use to test this in models such as ELM, get better constraints on TET. And so hopefully at this point I've demonstrated some of the utility that water tracers might have. The downside is that they can be really expensive. And so the version of CAM that I've been showing results from, adding isotope tracers to the code, increases the model cost by about 50%. And then if you just want to trace a few other properties, you can easily get to 4 or 6 times greater. So this became prohibitive, but this problem has, I think, become much less severe in EPSM based on advancements made to the tracer transport code. And the newer dynamical cores than the one that I've been using in CAM, which was the finite volume. And so, for example, Bradley et al. 2021 showed improvements to the EPSM atmosphere model, reduced the tracer transport and computational cost by about a factor of 3. At the same time, the data sets available to use for model tracer and isotope ratio validation, or for use in data assimilation or process studies, has exploded, which gives us a lot more opportunity. So for the first few decades of water isotope ratios, IAEA was really kind of the only game in town. And they were the primary source of these isotope ratios, but new observational campaigns and data sets have provided new opportunities. So for one, there are community databases such as waterisotopes.org that have come about that now house several 100,000 water isotope measurements. Water vapor isotope measurements have also become more tractable. And so there are remote sensing networks such as TCON and Musica and IAZI that are ground-based, or satellite sensors now measuring HDO in the atmosphere, such as Tropomi here, or GOSAT, or TESS, and there are many others. And there are also site-based networks, including the NEON towers, which have a data sharing agreement with Ameriflux, and a few ARM campaigns, such as Tracer, that have included water vapor isotope ratio measurements in their instrument packages. So this allows us to measure these measurements or investigate these processes at an unprecedented time resolution. And so one of the ideas I'm really excited about is to expand this tracer capability into E3SM, include the types of water tracers I've discussed today so that we can use them to their full potential. And so I'll wrap up the schematic here that I'm showing attempts to illustrate three things. One, there's a vast array of ongoing, existing, and freely available isotope ratio data with which to improve model validation of hydrological processes, and can connect them to ongoing diagnostic packages that have been built. Two, we can use these capabilities in the model to better understand and constrain hydrological processes that explain the observations. And then finally, these techniques can be used to clarify what we still don't know and motivate the next generation of observations. And so I'll put the conclusions up and I'll stop here to leave a couple minutes for any questions that might be there.